All right, so good morning, everyone, and welcome to the Climate Data Collection and Analysis Workshop. We are very glad that you guys could join us, especially some of you on rather short notice. I even had a couple people email me last night begging for a last chance to come to the workshop, so I'm very pleased that there's so much interest in the topic from your guys' side. So just quickly about us who will be doing the workshop. I'm Taylor Smith, and I'm a researcher at the University of Potsdam in Germany. And I've been working in high mountain Asia for the last, I guess 10, 12 years, mostly focused on snow and water. With me is Dr. Bodo Buchhagen, who is a professor at the University of Potsdam, also in Germany, who has been working here in the Himalaya for twice as long, I guess, 25 years, something like this, with a lot of focus on natural hazards, so landslides, rainfall extremes, these kind of things. And we also have another colleague, Dr. Shakil Regmi, who's based in Finland, who unfortunately, or maybe fortunately, is at a wedding of his little brother today, so he will be joining us tomorrow. So this is the schedule for today. This is also in the document that I sent you guys. First, we just do a little introduction to the goals of the workshop and talk quickly about the computer setup. And we'll spend a few minutes making sure that any questions and problems on that side are dealt with. Hopefully, Bodo will be while I'm doing some of these talks, he will be around, floating around. If you have questions about the computer stuff or you have a problem with installing something, please feel free to put your hand up and grab him. After this, we will talk for a bit about satellite climate data. So both Bodo and I work a lot with satellite data. I'm more focused on snow, and Bodo has done a lot more work with rainfall and natural hazards. So he will also talk for a bit about some of our previous work around high mountain Asia. Then we'll have a coffee break, and we'll get into some of the practical exercises. So up until lunch, we'll work first on some online data processing, and then we'll have lunch and another example, again with the online data. And one more coffee, and finally a third exercise, which is focused on how do we take this kind of data and make a nice visualization or something that's consistent if you want to have a report every week or every month, things like this. So that's the main focus for today. So focusing on satellite data and some practical examples of how we can use it without having to download and process a lot of data on our own machines. So sending all the hard work to someone else's computer, basically. So this is then the main goals for the workshop. We want to definitely provide some of our background knowledge on climate and climate change throughout the Himalaya and the bigger high mountain Asian region, and especially with a focus on satellite tools and how you can use satellite data to help understand the environment, especially with water resources. So I know many of you guys are coming from the hydropower sector, so I'm sure that this is the interesting side of things for you, understanding what we can get, what information we can get about water resources from space. From that, we want to also get some hands-on experience, so how to actually do some of this analysis. And then tomorrow, the focus is going to be more about hardware. So going beyond what's available on satellites, but how can we actually design and build and analyze the data from our own sensors. So in the last years, there's been quite a lot of developments on this very low-cost hardware. Many of you have probably heard of Raspberry Pi. This is quite a famous one, which lets you basically have a very small computer that costs 20 euros that can do a lot of these kind of tasks and analyze environmental data for you. So we're going to talk about some of the practical side of this and actually show you some of the things that we have built and have been installing in Nepal. And then finally, we'll wrap it up with some of our ongoing research and also ask you guys some questions about what data gaps are you guys see in your work, and how you might want to integrate some of the stuff that we've talked about in the workshop. All of the workshop data and materials are here on GitHub. I've put all of the exercises and the data on there. So you can download them. I can actually, well, when we start looking at the exercises after the coffee break, I will open that up and show you exactly where the data is. The data is not very big. Don't worry about downloading several gigabytes of data. It's quite small. And the exercises are rather small as well. Yeah, so I'm going to talk for a few minutes now about snow remote sensing, and then I'm going to pass it over to Bodo, who will talk more about, I guess, rainfall and landslides and these kind of things. So I'm sure you guys are all quite familiar with snow. It's everywhere around, and it's a particularly difficult thing to measure in the environment like the Himalayas, because it's very, very hard to get up to a lot of these places where the snow is, right? If you think about, even now, you go to 3,000 meters, maybe there's not so much snow, and it's a lot more difficult to get to 5,000 meters than it is to get to 3,000 meters. So it's very hard to do these direct measurements and understand how deep the snow is, and even how much water is stored in the snow. Rainfall is somehow easier to measure because you have, you can just measure how much of it is coming into a bucket, and that gives you an idea of how much it is. You can measure how many water particles are in the atmosphere. This works pretty well and is well established. Snowfall is much, much more difficult. You really have to measure it once it's on the ground, and there's a lot of difficulties that come into that. And it's also something that's quite important. So these two charts on the right-hand side here is basically what the snow cover looks like in the whole northern hemisphere throughout the year. So we have more snow on the ground in February and less snow on the ground during the summer, right? We go from the winter to the summer where there's less snow and again more snow. That's pretty obvious. What isn't so obvious, or was not so obvious to me, is that this sort of seasonal pattern is not something that's stable. So if we look at how that pattern changes over the last 40 years, there's actually a lot less snow in the summer, but there's also more snow in the fall and up until January and February. So there are a lot of places that are getting much more winter snow, but then it's melting a lot faster. So the timing of where and when snow is falling and how much of it is stored as water is changing quite a lot. And the main reason for this is air temperature. When you have warmer air temperatures, it can hold more water. And that means if that warm air that has more moisture in it goes somewhere where it's already really cold, then it still becomes snow, right? If your average temperature is -10, then it doesn't matter if it's -9 the next year, right? Then it's still cold enough for it to make snow. On the negative side, however, of course, there's earlier snowmelt from warmer temperatures. More snow falls as rain, especially in lower elevations. And you also get more of these rain on snow events. So rain that falls directly on snow and melts it out quite quickly. So the timing and the pattern of snowfall and snow water storage has been changing over the last decades. And of course, especially in this region of the world, water that is stored in the frozen form, so as glaciers and as snow, is extremely important. Not just for because we like having glaciers, they're pretty to look at, but also because they're a real big reservoir, especially during the summer, right? Before the monsoon comes or after the monsoon, when there's just meltwater coming from these really high regions. If there's no more snow and no more glaciers up there, then you can have these dry periods. So even if you get the same amount of rain throughout the year, if it all comes at once during the monsoon, you can have 6 months with just dry. And if there's no snowmelt coming down, you can have real problems, especially at high elevations. And this is something that's really important in this region. If you look at these blue and red balls here, this is basically how much, the red is how much water comes from rain, and the blue is how much water comes from snow and glaciers and ice. And here, our region of high mountain Asia is where all those big blue balls are. So there's a lot of watersheds that get, half or 2/3 of their water from snow. So changes in this are really important to track. And also just the amount of water that's stored here in the Indus and the Ganges and up in the Tibetan Plateau is massive compared to the rest of the world. So it's a real thing that needs to be focused on in this region. I always like to put this slide up just to emphasize, I'm sure you guys are all quite aware of how the monsoon comes in the summer, and then the winter precipitation comes in from the west. When we're talking about rainfall, we're mostly talking about this one, so the monsoon coming up along. And winter snow is mostly coming from this direction, so coming down along and up along this edge. And this is something that we can get from satellite data. And this is something that we can do pretty well from these satellite rainfall and snowfall missions. However, if we want to actually look at measurements from weather stations on the ground, we have a really sparse picture. So maybe down, in the plains here, we have quite some weather stations. But if you're looking up here in Tibet and up in the higher elevation regions, there's just not very many climate stations, right? It's very hard to get up there. It's very hard to keep something powered up there and to actually send the data. Hiking up to 5,000-6,000 meters to go, download data once every few months is quite a task. So there's a big, basically, gap in how much real on-the-ground information we have. So this is one of the main reasons, especially for these high elevation regions, that we start relying more on satellite data to try to look at snow. So when we talk about using satellites for snow cover, we basically have two options. One is just to look at how much area is covered with snow, right? Is the ground covered with snow or not? And then you get an idea of how much area is covered with snow. And this is something that we usually do with visible light. So basically, during the day, you can look at the ground and see if it's white or not. That's pretty much the principle. It's a little more complicated than that because, of course, we look at a few different wavelengths. But essentially, we're taking pictures and looking to see if there's snow. So that means that it doesn't work if we have clouds. So if we can't see the ground from space, then we don't know. So in times where there's a lot of clouds, it's hard to say if there's snow or not. And we can't really do this at night. So sometimes we have big gaps if we have a long period of clouds or other problems. You can get data potentially every day, but it's more often that you get snow cover data on a weekly basis or monthly basis. And this ranges quite a lot in spatial resolution. So a lot of products are multiple square kilometers, which can also be difficult when you have a really complicated terrain like we do in a lot of parts of the Himalaya. If we take the long-term average, so this is from one of the main snow-covered area products, just showing this is, of course, Tibet and the Himalaya coming up here. This is basically where we have winter snow cover. So this is just the average winter snow cover going up to 70, 80, 90% here. And you can see that there's quite a lot of area where we have snow cover. But thinking about the spatial resolution here, if you're looking at a very small catchment, this doesn't always cover exactly what you need to know. And if you have data gaps, like making a nice map like this for the whole season is great. But if you need something for a week or one specific day, it can get a little bit trickier. So the other way that we usually look at snow is with passive microwave data, which you don't need to worry about exactly what that is. How it really works is that the Earth is always emitting some radiation. So anything that's warm is emitting some radiation. And when you have two different frequencies, one goes straight through the snow, and one hits the snow and gets dispersed. So the signal gets weaker. And that ratio between the direct signal and the sort of weakened signal gives you a good estimate of how deep the snow is. And from that, if you know how dense the snow is, you can turn that into water. And this pretty much looks like this. This is from somewhere in Tibet, I don't remember exactly where, that you get these two different signals, and their difference then tells you how much water is actually stored. The nice thing about this is that it works through clouds. Clouds don't really impact it, so we don't have these same kind of data gaps. The bad thing about this is that the spatial resolution is much, much less. So it's like 25 by 25 kilometers. So if you think about how much things can vary in your terrain in 25 kilometers, it's nice for making big area averages, but can be a little bit difficult to work with, especially if you're in a small catchment. If you're looking at how much water is being stored in the whole Indus, perfect. If you're only looking in some little corner, then it gets a little bit more difficult. So this is from some passive microwave data. This is some work that Bodo and I did a couple of years ago, looking at how snow water storage is actually changing throughout high mountain Asia. All the blue stuff here is positive, so areas where there's actually been more water in the last 40 years, I guess since 1987. And the green and brown stuff is where there's less. So if you look at this, it's really the highest elevation parts. So up here in the Kunlun, parts of the Pamir, and the Altai up here, and the highest parts of the Himalaya, you're actually having more water stored in snow in the last years. So this is exactly this relationship that I was talking about, where when it's already really cold, it doesn't get warm enough to melt the snow. And when you have more moisture, you still get more snow. The places where it was closer to freezing, where it only sometimes had snow, or you're right around zero, there's a lot less snow being stored. This is also changing quite a lot from season to season. So now the blue stuff is negative, so loss of water, and the red is positive, so a gain of water. And this is the winter, spring, summer, and fall. So the big thing here is that we see a lot of red in the winter. So in the winter, we're getting quite a lot more snow in a lot of places, except, of course, here where we're having things have warmed up too much, and even in the winter, they're not really getting so much snow anymore. So those guys who are managing the water coming down the Yellow and the Yangtze are going to have some problems in the next years. Also in the spring, we still have some more, but then when we get to the summer and the fall, it's a lot more negative. So we're getting more snow that's coming in the winter, and in a lot of places it's melting a lot faster, like up in here, it's melting a lot faster. But still, some of the higher elevation places are storing more water. Just to make this one more step complicated, this is also changing from decade to decade. So if I only look at the 1980s, everywhere is losing snow. It's all blue. It's all bad. And if I only look from 2006 to 2016, it's mostly red. So it's actually mostly gaining snow. So it's a little bit difficult to say how things will develop in the next years, if it's going to continue more like this, or if it's going to continue more like a loss of snow, or if it's doing a big cycle every 10 years. And this is something that we're just going to have to wait and see until we get more data. The main point that I wanted to make here is that it's complicated, and it's not a straightforward, there is climate change and we lose snow. There are a lot of places where there will be more snow, and also times and years, seasons when we have more and less snow. So it's important to not just assume that everything's going to disappear, but to look at the data and also look hopefully more closely with more weather stations, these kind of on-the-ground data, to see how things will develop in the next years. Yeah, so just to wrap up the snow segment here, there's still a lot of gaps in our understanding, especially at really high spatial resolutions. So these maps that I'm showing here, these are really, really big areas that we're talking about. This picture looks a lot different if you zoom into a small area. And we can definitely use some more spatial and temporal resolution. It's very useful for long-term trends, but looking at how exactly things will develop during a single snow season still is difficult, and it's helpful to have more on the ground data.
Hello everyone again. You may be wondering why we are moving the microphone around. We are recording this session. We are planning to put things up on YouTube later the day. Let's see how that works out and what the quality of the recording will look like. The idea in the next 30-40 minutes is to follow up on what Taylor has been starting with a snow introduction, and I wanted to talk a little bit about how we can observe hydrologic components in the Himalaya. So this will be focusing much more on the Himalaya, and I will also be bringing in sediment flux. And my understanding is that most of you come or work in the hydropower sector. So in other words, that you have some kind of a connection to energy generation or water storage in the mountains. And one of the problems that we encounter in those areas is not only changing water amounts, but also changing sediment flux amounts. And what I would like to do is briefly making two statements about sediment flux, because that is something that will impact a lot of hydropower plants and also hydropower energy generation efforts in the near future, because we are eroding more sediments from the hill slopes that will fill in those reservoirs much more rapidly. So sediment transport from mountains through rivers to the ocean is an important component of the natural cycle of mass and nutrient transport. These processes are key to form and maintain fertile floodplains. So essentially that statement means that without sediment flux, there would be no Ganges plain and there would be no area that would produce rice for the global population in that sense. So sediment flux is a good, it's a good thing in that sense, because it brings in nutrients, the weathering products from the mountains to the foreland. But sediment transport from mountain ranges and their changes through time are not well understood and have significant implications for downstream populations, ecology, and water resource management. Meaning that if you have higher sediment flux in your rivers, your reservoirs are filling up much faster, and there are some hydropower plants in the Western Himalaya that are also turning off their turbines when the sediment flux exceeds 2 milligrams per liter. So that's that's kind of a threshold where the higher sediment flux then would abrade the turbines too much, so you end up turning off the turbines, meaning you're not producing any energy during those higher sediment flux events. And you kind of want to understand those events better. So let me give you a quick view of what the global distribution is of suspended sediment to the coastal ocean. It is inherently difficult to measure sediment flux. So it's not something that is as easy to measure as temperature, where you have a physical property that you can measure with a device that records the temperature, the ambient temperature. Sediment flux, measuring it in a river is fairly difficult. Taylor will be talking about this tomorrow in more detail, how sensors can be built to measure sediment flux. But irrespective of the fact that it's difficult to measure, we see that the global distribution of suspended sediment flux to the ocean is clearly dominated by high mountain Asia. And that's mostly related to the high weathering rates and to the steep terrain. So the steeper the terrain, the more sediments you can produce. And the warmer the climate, the more weathering you have. So that's why the sediment flux here in this area is much higher than on other continents, which also is an extra challenge to the hydropower plants that exist in this part of the world. And I'm now showing in older slides of the large reservoirs that exist. And if we, this is from 2003, and if we would do this again for the Himalayas, you would see that there would be many more large reservoirs that have been built in the last 10 to 15 years in the Himalayas. So this, particularly this area, is currently the hotspot of hydropower generation. You have a lot of water, you have the monsoon, you have snowmelt coming in, but at the same time you have high amounts of sediment flux, which shortens the lifetimes of some of those reservoirs or make it more difficult to maintain them. Okay. Just a few more things about sediment transport. I mentioned that it's difficult to measure, similar to snow cover on the ground. The problem with sediment transport is that it's a stochastic event-based process, meaning you can have the river flow can be a week without or very low sediment flux, and then you have a couple of hours of very, very high sediment flux that is orders of magnitudes higher than you have during the rest of the week. So this is then a sediment flux event. And Taylor is going to talk more about event-based analysis throughout this workshop, because many of those impacts that we are looking at, flooding, sediment transports, these are very event-based, meaning that you have a normal state for 99% of the time, and then at very short time intervals you have a lot of water or a lot of sediment coming down the mountains. And that makes it inherently difficult to measure those events, because if you miss that event, if you only go out once a day to sample sediment transport or sediment flux, you would be missing that big sediment flux event. So it is very important to have a high frequency of observations. That's where the in situ sensors come in. I just talked about the fact that sediment transport measurements is very difficult in steep mountain terrains, mostly because if you put in an in situ measurement in a river and you have a big flood coming, that device gets taken out, right? I mean, you all have seen floods in the Himalayas, right? I mean, if you have a big flood come down the mountains, it just takes away everything.
If you put something in the water,
everything will be gone. So it's very, very difficult to measure those events. Okay, let's talk a little bit about the climatic forcing. So I'm going to talk more about rainfall in the next 10 minutes, and then I'm going to talk about discharge components of the Himalayas. And I'm going to focus on the Himalaya, not that much on high mountain Asia. So for me, the Himalayas are between Pakistan, India, Nepal, Bhutan, and maybe a little bit of China, also Tibet, as that definition doesn't belong to the Himalayas anymore. So what I'm showing here are the big catchments, the catchments that drain to the south. This is what I consider being the Himalaya. Where you have not the internally drained part of Tibet, but the part that drains either through India or through Pakistan in the far western section. We heard about the climate system just a few minutes ago. We have the Indian summer monsoon bringing in moisture from the Bay of Bengal, and it's being transported along the mountain front. And we have the East Asian monsoon. So those are the two summer drivers. In the winters, we have the winter westerlies that bring in precipitation, mostly in the form of snow. So this is where the snow cover comes in that Taylor just talked about. So when we use satellite data to derive a longer time series, and we take an average, for example, a 20-year average of rainfall, now using an active precipitation radar, we see an interesting pattern emerging. We are seeing that there is a high rainfall band. Blue color is high rainfall, red color is low rainfall. So we see that there is a band of high rainfall at the foot of the Himalayas. This is an orographic barrier. This is where you force the rainfall to rise. The air is cooling. When air is cooling, it loses the ability to store moisture, and rain runs out. So this is the first, I always call it the first rainfall band, and then we have a second rainfall band, particularly here in Nepal and in other areas of the Himalayas, and that's just the second topographic step that occurs. It's the second orographic barrier that occurs. So these are the two pronounced rainfall bands, and they only come out with a high resolution data set. If you use a coarser 25 by 25 kilometer resolution data set, it does not display that well. And we also see the Shillong Plateau here, which is some of the wettest places on Earth, with a record rainfall of 11 meters in 1 month. So that's certainly a very wet and drenched place. Let me point out what, on the big scale, what the monsoon is responsible for. The monsoon drags or draws in the moisture, making this the wettest inhabited place on Earth. And if we go along the same longitude, along the same latitude, going to a different longitude, we are in a desert region. So this is a typical geographic setting for this latitude. Around 30 or 25 north, we have deserts all around the globe. And that's a typical setting. The monsoon allows us to bring in a lot of moisture that then drenches this part of the mountain range. Let's look at this rainfall barrier in a little more detail. I pointed out that when we go from south to north, we go from the foreland areas, here those black lines, that's a swath profile. The black line goes from the Ganges to the Tibetan Plateau. And what we see in blue is that profile of the rainfall. So that peak rainfall is that rainfall peak that we observe that's related to the orographic barrier. So rainfall is not evenly distributed in the mountain front. You have peak rainfall, and this is also where the flooding would be initiated, right? So if you have high rainfall amount, that's the location where the flooding is being initiated. We can simplify that in a conceptual model, and I will be coming back to this. So you have increasing elevation, you have a threshold elevation, and you have rainfall occurring at a specific point. If you come from a modeling perspective, you can also think about relief as a driver of rainfall. So where you have the maximum relief, you have the rainfall peak. So this is a very simplified model to understand rainfall distribution in the Himalayas. Now, when we go in the Nepalese Himalaya, we have a two-step topography due to the different tectonic evolution in that part of the Himalayas, and we have 2 rainfall peaks. And so we trigger flooding in different areas of the Himalaya. Now let's ask the question, what happens when we have a stronger monsoon season or when we have a stronger monsoon storm? During the normal setting, we see one rainfall peak that occurs here at roughly 1 to 2 kilometers elevation. When we have a particularly large rainfall storm coming in, we are not increasing the rainfall peak. The rainfall peak is already saturated. We can't make the peak higher, but we can bring in moisture into the origin. So we are bringing it further into the Himalayas. So in other words, there are parts of the Himalayas that receive rainfall that are usually dry. And then, of course, the water gets routed through the river system, and you cause downstream flooding. And if you put that into the landscape, we are at the rainfall peak. We have the densely vegetated, rich soil layers landscapes where you have a lot of infiltration occurring, where you also have a dampening effect of the rainfall, right? So you have not necessarily all rainfall is immediately running off. You're dampening it through the canopy layer. When we bring in the higher elevations, you have a lack of canopy layer, you have no or very little soil development. And now if you bring in that big rainstorm into this area, you are turning on the sediment transport machine, right? So if you have a big rainstorm occurring here, you can envision that those hill slopes will produce a lot of sediment that then gets routed downstream. And this is the cause for many of the very high sediment flux events that occur throughout the Himalaya, that you bring in a rainstorm into the deeper part of the origin that is usually dry, and you can erode material much more rapidly and then transport it downstream through the fluvial system. So that's something that can be said for every catchment, but of course there are catchments that are more prone to those large sediment flux events, and I will be showing a few examples in a couple of minutes. I just wanted to show one example of where rainfall migrated further into the origin. This is an example for an exceptional large mesoscale convective event that occurs in 2010. That was the Pakistan flood in 2010. That was one of the biggest humanitarian disaster with more than 10 million people that has to be displaced. So this was a major migration event also within Pakistan. It's already 12 years ago. I'm still bringing this up. And what I'm showing here in the colors is where we had the most extreme rainfall occurring. And this is occurring in the areas that are usually dry. So these areas here in the upper upstream sections, they are usually dry, and those areas experience the highest rainfall during this particular flooding event. So this is an example of a major mesoscale convective event that propagated very, very far into the mountain range. When we look at a modern data set and we look at the 10 largest rainfall events for every pixel. So now think about you have a 5 by 5 kilometer area and you're looking at the 10 largest rainfall events. So these are the extreme events for every pixel, and you compare it to the total rainfall amount in this pixel. So in other words, how important are the 10 biggest events compared to the rest of the rainfall? And what we see here is that in the areas to the north of the orographic barrier, you see those red colors here. Those red colors, just to the north of the orographic barrier, we have the strongest rainfall events occurring. So in other words, the rainfall is made up only out of extreme events. So whenever a rainfall comes in, you are increasing the discharge rapidly. And now look at those black lines. These are the catchments. You see that some of those areas that receive those extreme rainfall events, they are first of all north of the border. They're in Tibet, so there is no information for the Nepalis to be gained at this site. That's just the political boundaries that we have, but they're still part of those catchments, meaning that if you have rainfall in those parts, it makes it very, very difficult sometimes to predict the downstream effect. I just wanted to point out that it's really important to look at those dry areas, not necessarily the wettest areas that receive continuously rain. It is partly the dry areas that cause the big destructive events. And I just wanted to come back to what Taylor said earlier and briefly point out that it's not only rain that falls, but at the mountain front it is mostly rain. So the blue colors here mean that what makes up the water budget. The blue colors mean more than 95% is rainfall, which we would expect at those elevations, right? We expect that the frontal regions mostly receive rainfall. When we go into the mountain areas, we see that the colors turn more greenish and maybe even yellowish, and that's where you have 30 or 40% of the precipitation occurring as snow. And measuring snow is very, very difficult, as we just heard. And so predicting what the discharge is from those areas that have a higher snow cover is still challenging. This is a zoom in of a figure that Taylor was showing earlier for the global scale. This is a scale of high mountain Asia. And again, the orange colors are the rainfall component, and the blue colors show you the snowmelt component. And you see that the Ganges area is mostly dominated by rainfall. But if we go to the catchments in Central Asia or into the Tibetan Plateau, we see a much, much higher snow component. So for those catchments, it is very, very important to understand the snow component as well. But don't be mistaken. Even so, I'm saying this is mostly rainfall. There can be catchments that are smaller catchments in the Nepali Himalayas that are only driven by snowfall. So this is, this is inherent in here, that there are small catchments that can also be driven fully by snowfall. I just wanted to point to the fact that it's a very complex picture. Now let's ask the question, where does the water come from? And I'm going to show you an example of real data and modeling study using snow cover data, the rainfall data that I was just talking about, and in evapotranspiration data set. And I'm looking at two different catchments. One is in the far west, this is the Indus catchment, and then one here in at the border between Nepal and India, the Tista catchment. So the Tista catchment is an example of a monsoon-driven catchment, and the Indus is an example of a glacial or snowmelt-driven catchment. So we have the annual hydrograph. This is from January to December, and this is the amount of water that comes down. Note that the magnitude on the y-axis is basically an order of magnitude difference, meaning that we have 10 times as much discharge in the Indus than in the small Tista. So that's not surprising. If we bring in our rainfall model, and we see what the seasonal distribution of rainfall is, we see that we can explain some signal of the discharge through runoff generated by rainfall. In the Tista, it matches pretty well the actual measured discharge. If we bring in our snowmelt model, how much material or how much water is derived from the snowmelt model, we see that we have an earlier peak. Usually in April or May, you have that snowmelt peak that brings in most of the water, much more water than rainfall at this time of the year. So the earlier season, April, May, is usually dominated by snowmelt in many of the Himalayan upstream catchment or the Indus total. And if we use if we bring in the evapotranspiration, we see that there is an increase of evapotranspiration just due to the temperature increase in the August timing. And if we put this together, the Indus catchment, the discharge of the Indus catchment can be explained by essentially two peaks: rainfall peak later in the season in August, and a snowmelt peak earlier in the season, usually around May, that makes up the total discharge. You can also bring in the glacial melt that then would be important for the later season as well, so the September season. In the Tista, the situation is a little different because you have a catchment that does not cover a large area with snow cover. Most of the discharge can be explained by the rainfall distribution. If we would go to the Arun in Nepal, you would have a different picture because you have a higher snow cover in the upstream Arun section. So that's just as a temporal distribution of the hydrologic components. And if we put that into numbers, we see that there are some catchments that have a very, very high snowmelt contribution. That's the western catchments that receive a lot of the winter westerly precipitation in the form of snow, mostly the Indus and the Sutlej, with way more than 50%. And if we look into the Arun and the Sangpo, for example, that also cover part of the Tibetan plateau, then we see a higher contribution as well. And then most of the frontal catchments only have less than 25% of snowmelt occurring. Let me just say a few more words about sediment flux. So we are moving away from the large-scale river view and look at sediment flux, and I'm going to focus on a very specific catchment in the Western Himalaya that I worked on for many years, and I also did my PhD in that area. That was now 20 years ago. So I'm going to talk about magnitudes of sediment transport. I'm going to show the impact of a rare flood. So we were able to record a rare flood in the mountains. And I'm briefly pointing out that the sediment flux changes through time. So the same what Taylor was saying, from the 80s to the 2000s, you have a change in the trend of the snow cover, is also something that we observe in the sediment flux, even on longer time scales. So we are going to zoom in the Sutlej, which is the third largest catchment in the Himalaya, and it later on joins, or further downstream, it joins the Indus, but it is the third largest catchment draining the Himalaya. And the Indus has that typical setup that the mountain fronts are very, very densely vegetated. So this is the NDVI, another remote sensing-based vegetation data set. So the green color indicate the denseness of the vegetation. You have a very dense vegetation cover in the frontal region, and then a lot of the upstream part is vegetation free, right? This is a typical setup that we see in many of the Himalayan catchment. And I'm going to show you data from two catchments where we worked with the local hydropower companies. One is the Ganvi catchment, which is exactly at the rainfall peak. So this is an area that receives a lot of continuous high rainfall. And then the other example here is from the Baspa Valley, which is at the tail of that distribution. In other words, that receives episodic moisture. This is not a very densely vegetated area. And now I'm showing a graph where I'm hoping you are familiar with the axis labels. So we are looking at river discharge versus suspended sediment concentration. That's the typical graph that you use to estimate sediment transport or suspended sediment transport. And that's a logarithmic plot. So we are going in orders of magnitude on the x-axis and on orders of magnitude on the y-axis. So going from here to here is a 10 times increase in sediment flux, and going from here to here another 10 times. So going from 10 to the -2 to 10 to the 0 grams per liter is it's a factor of 100 difference. And what you see is that, generally speaking, there is a power law relation between discharge and suspended sediment concentration, meaning the higher the discharge, the higher the suspended sediment concentration. I think that's textbook knowledge that most of you are familiar with, right? But there is a reason why I'm showing this plot, and I'm showing those plots, and I covered some of those dots red. You see there are some measurements that we took in the field that are way outside the expected regression. So those red dots are the extreme suspended sediment concentration events that would not fit into this general model. And those events occurred after a very, very heavy rainfall event. So they may be related to the first storm in the season, when you excavate most of the unconsolidated sediment that sits up there, but you essentially generate sediment concentration an order of magnitude higher than you expect, right? For a given discharge, you have a given discharge, and now you have an order of magnitude higher suspended sediment concentration because of that extreme event. So understanding those events is a challenge, and it also makes it difficult to measure them. And if we go into the partly dry area, now we are going into the Baspa River that receives even more episodic moisture, where we have no vegetation cover. Those extreme events are 2 orders or even higher than the expected event. So these events, there may be only a handful a year, or maybe only 2 a year, but those are the most destructive events that can take out or that can render a hydropower project destructive for a couple of weeks or months. We have observed such an event ourselves that caused great havoc to the largest tunnel hydropower plant in the Sutlej that we worked with. So those are the extreme events that are for the same discharge, that are much higher than you would expect them to be, or that your regression predicts them to be, and those are then the destructive events that cause the problems. Okay, Let me just wrap this up by pointing out that sediment transport changes through time. And I'm putting together a compilation of different measurements that we have done for this Baspa catchment. And in the Baspa catchment, we have present day measurements. So what you see here now, this is maybe not the most typical plot. What you see here on the x-axis is time before present in logarithmic steps, meaning that this is 10 years, 100 years, 1,000 years before present. And here we have the erosion rate, so how much sediment is being transported. And the length of this bar indicates over what time scale is being averaged. So we have an modern annual measurement taken from the hydropower company that is about 30 years long. For the 30-year average, we have an erosion rate of 1 millimeter per year. So everywhere in the catchment, you're lowering the catchment by 1 millimeter per year. It's a high rate, but it's not extremely high. It's still okay in that sense. If we use cosmogenic nuclides, that's a geochemical method that includes also the extreme events and has a longer time scale, we see that for the same area, we have an erosion rate that is almost 3 times as high, because that record also includes the extreme events. And I know from experience, when there is a high sediment flux event in the present day, and usually you go out in the field, you go on the bridge, you lower the bucket into the water, you take the 10 liters and you measure the sediment concentration in there, right? If you have a big storm and a high flood going through, you're not going to go out on the bridge and take a sample from the water. So you're clearly missing the large extreme events, and those are included in here. So our real erosion rate may be even 3 times as high. And now we can take it a step further and ask the question, so what if we go a couple of 1,000 years into the past, where we know that the monsoon has been stronger? So we know there have been intensified monsoon periods. For example, in the early to mid Holocene, we had a monsoon optimum where the monsoon was much stronger. And if we take a sample from a landslide that occurred during that time, and we estimate the sediment flux by the lake that formed behind that big landslide, we have an even higher erosion rate during those intensified monsoon phases of roughly 4.3 millimeters per year. So we have a wide range of erosion rates going from 1 millimeter per year up to 4 millimeters per year that are all in that reasonable range of measurements that have been done. And if you do an assessment of a hydropower plant where you assume an average erosion rate of 1 millimeter per year, you do get a very different reservoir filling rate than when you do use 4 millimeters per year. So it's very important to consider that dynamics of the sediment flux that occurs. Okay, I think this is all I wanted to get across. I just wanted to briefly motivate you while we are interested in measuring sediment flux and or river properties at a high frequency. And I think we can come back to those discussions in the last day and bring up some other examples like landslide tracking and other features that are associated with sediment flux.